Thank you very much. I'm really happy to be here, and I'm really happy to have had such a good introduction to exoplanets and exoplanetary systems this morning. So I'm really interested in the fine details of what planets are made from, and how that can tell us about what those planets are like and their potential for habitability. And what I'm going to talk about today is thinking about what we've done for decades with our solar system in terms of cosmochemistry to learn about the fine details of the solar system's history and how we might be able to kind of apply some of those insights to exoplanetary systems. Does this change slide? Yeah. Okay. So we've had a great highlight of how we are discovering lots and lots of more exoplanets, and we're moving down to smaller and rocky planets. And if we truly want to understand what those planets are like, we really want to know what their interiors are like, we want to know what their atmospheres are like, and ultimately we want to know whether they're rocky planets that can host life. But this is really, really tough, and I don't need to be the first person to tell you that. Normally for exoplanets, we just have a mass and a radius, and we're really struggling to even kind of get to the point of here kind of splitting the exoplanet up into these kind of thin models where we just have a very simple kind of layers between core, mantle, and crust, and saying that categorically is what this exoplanet is like. But actually, if we want to understand truly the geological evolution of a rocky planet, we don't need to know just whether it has a crust and a mantle. We need to know what that mantle is made from, what are the silicates and the magnesium, what are the silicates like, and how does that lead to the evolution? So how can we kind of think about doing this? Well, fortunately, if we think on galactic scales, we know that stars and planets both form out of the collapse of the same material. So if we kind of think about through kind of the history of the universe, we have the enrichment of star-forming regions with metals as kind of the universe evolves. And both the stars and the planets that we're forming, they're going to form out of that same initial cloud of material. And that material will have a particular composition and a particular availability of the species that we need to form planets. And so maybe we can use that unique insight to help us in terms of composition. And we actually do this in the solar system. It's something called the chondritic hypothesis, which says that the chondritic meteorites, these are some of the most primitive meteorites that we know in the solar system, and we know their composition super well because we can handle them in the lab here on Earth and to use mass spectrometers, that actually they have the same refractory composition as the sun. And so this plot is showing the composition of the chondrites against the solar photosphere. And you can see that in general, for most refractory species, that there's a really good match between these two. The match stops working when we get to the volatile species, and those are the ones that are really highly processed during planet formation. And what's nice is that we can then use, as a cosmochemist, we can use these chondrites to study different kinds of meteorites, and we can compare the composition of those meteorites to these chondrites in the context of this kind of hypothesis, that they started off with this same refractory composition. So very simply, we kind of say, well, maybe planet equals star in terms of refractory composition. But does this work for exoplanets? Or is there something crazy that can happen during planet formation that can really change some of these things? And we know, even from the solar system, that this works for chondritic meteorites because they're primitive and unprocessed. It doesn't work for meteorites that have been processed, and we have to understand those processings that happened during planet formation. But if we use this assumption that planet equals star, it massively improves our characterization of the interiors of those planets. It helps us to say, when we have just a mass and a radius observation, it helps us to say really what that planet might be like on the inside. So it's a really important assumption. And so what I'm going to talk about in the next kind of 5 to 10 minutes is how we can test this from an exoplanet point of view. So how do we compare planet and host star compositions? Well, we're going to do that uniquely by using binary systems. So if we imagine that we have two stars that have formed together, they form out of the collapse of the same cloud of molecular gas, so they have the same initial abundance of material there. One of the stars is more massive, and so it evolves much faster. It has planets, and then it evolves to become a white dwarf, whilst the other star is much less massive, and so is left behind on the main sequence. And so if we're able to observe these systems at the point where we are looking at a main sequence companion at maybe a few thousand AU, around a white dwarf, we have a unique opportunity to ask the question of, like, does the planet and the host star abundances match? And that's because we can use the stellar abundances from the binary companion, and we can understand the planetary abundances from the white dwarfs. Okay, so let's take a big step back. So planetary abundances from white dwarfs, some of you I'm sure know exactly what I'm talking about, but for those of you who don't, white dwarfs are these amazing laboratories for studying planetary abundances. And that's because they, oh gosh, that was a mistake. They have these, sorry, they're very, very small. Oh, it's all gone wrong. Right. That's because white dwarfs are these tiny little stars, faint remnants of stars like our sun. Is it showing the right thing? And they have these small, sorry, everything's collapsed. So they're about the size of the sun, but they're about the size of Earth, but they still have about the same mass as the sun. And that means that they have very, very high surface gravity, and they have these very thin atmospheres. So here we can kind of see, so the atmosphere is on the order of tens of kilometers thick. And anything heavier than hydrogen or helium in the atmosphere of that white dwarf sinks out of sight on timescales that we can estimate theoretically of days to millions of years for the coolest white dwarfs. And so we expect white dwarfs to have these pure hydrogen helium atmospheres. And yet when we observe them, a small subset of them seem to have elements heavier than helium in their atmosphere. And so what we think is going on is that these white dwarfs have accreted planetary material. This is an outer planetary system that survived the star's evolution to the white dwarf phase, and there is some occasional scattering of comets or asteroids that end up with a small amount of material, maybe 10-kilometer sized body, in the atmosphere of the white dwarf, and we can see that in the white dwarf spectra. And these observations are a great way for studying what's going on in terms of exoplanet interiors. We're now at the point where we have kind of tens of objects where we have multiple elements, and we can constrain the major rock-forming elements that form Earth. So, for example, magnesium, oxygen, silicon, and iron here. And this is showing the kind of diversity that we see from white dwarfs that we can use to learn about planet formation, geology, volatiles, and what's going on in terms of composition in these things. And this is a really great time to be studying white dwarfs. So Gaia has recently identified hundreds of thousands new white dwarfs, or newly identified white dwarfs, which are readily accessible to spectroscopic follow-up. Okay, so back to the binaries. Well, what do we want to do? Well, we want to compare the abundances of the planetary material that's accreted by a white dwarf to its binary companion. And we first did this a few years ago for WD1425, and this is a white dwarf that's accreted something that looks like a Kuiper belt. So this is a cometary material. It's even volatile rich. There's water there. There's carbon and nitrogen detected. And we compared the abundances that we see in the white dwarf over here to the wide binary companion that's orbiting at about 2,000 AU from the star. What we found helps us to confirm that idea that the planet and the star abundances should match. So this is just kind of comparing the number of abundances of various ratios in the binary, which is our stellar companion, to the planet, which is the green. And we can show from this that they're consistent in almost everything, apart from carbon, which may well be depleted relative to iron. But that's what we see in comets in our solar system as well. And so it's helping us to learn about planet formation and action. And so this is a relatively new technique. We only have a handful of objects so far. But this is new work from Claudio Aguilera Gomez. He's just submitted this recently, which is showing another object where we're comparing the stellar abundances, which are shown here, helpfully with 3 points, but I'm told that the middle two are the better stellar abundances, to the white dwarf abundances, which again has 3 points, but if we just focus here for now on the green one. And here we're looking at silicon to calcium against titanium to calcium. And this object's even more interesting because not only do the refractory elements abundances match, so titanium and calcium between the white dwarf and the star are very similar, but we're seeing evidence of a depletion of silicon relative to calcium, which is evidence of heating, very strong heating that happened during planet formation. And that's helping us to constrain the thermal history of these kind of planetary bodies. And it means that around this host star, which is a much more massive host star than our solar system, this body's probably experienced temperatures higher than 1,400 Kelvin. Okay, so hopefully, it's been a bit of a whirlwind tour, but hopefully I've persuaded you that composition is really important for understanding exoplanet interiors, for understanding their geology and for understanding the potential for life. Host stars provide an awesome set of clues as to what's going on, but it's important to think about how planet formation alters the planetary abundances on the way. And white dwarfs that have accreted planetary material are a great way to study composition, and if they happen to be in a wide binary system, then they can really help us to test how planet formation works and how it changes planetary abundances. So thank you for your attention.